factors that affect the rate of your reaction are going to be concentrations, like you saw in the previous problem. If there is more particles present, they're more likely to collide. There's going to be more collisions, so your rate would be faster. There'd be a greater change in concentration over time. And we saw that as well in the graph when we saw the concentration was changing quickly and then slowed down. It's because you were running out of your reactants. The physical state matters as well. If you have a solid, the only particles that are available to react are going to be along the surface or the outside of the solid. The rest of the particles are hidden by the rest of your solid. If you have a powder, there's a higher surface area. If you have a gas, you have all these particles flying around, and they're more likely to collide with the other reactants and have a reaction. Temperature is going to be how fast the particles are flying around, and you can imagine if they're moving faster. If we remember, temperature was a way that we measure average kinetic energy. If your particles are moving around faster, they're more likely to collide with enough energy to overcome the activation energy. They're going to collide harder. They're also, since they're moving faster, they're going to collide more frequently. And finally, we have catalysts. What a catalyst does is it lowers the activation energy. So we said that particles have to hit hard enough in order to overcome the activation energy, unless you use a catalyst which will lower the activation energy. It will make it easier for reactants to react if they come in contact. So those are the 4 things affecting rates. And the reason we study rates is we want to see how concentration affects rate. And once we get what's called the rate law or the rate expression, then we can find out what the rate would be given any other concentration, as long as we keep temperature the same. The other thing we can do is we can find out how many times a reactant is likely to be involved in collisions in the steps of a reaction. So we can end up figuring out those steps. The reason we come up with, this step plus this step is really what happens as A turns to C. This is the overall reaction, because I can see I've got 1A, 1A, B, and a B. Overall, A goes to C. So you might wonder where we're getting these steps. We'll see that in lab. So we'll see that maybe A is showing up twice. So when you double the A, you're quadrupling the rate. And we'll see what that means. So investigating the relationship between concentration and rate of reaction gives us an idea of what the steps are, or the mechanism of the reaction. So the way we study how concentration affects the rate is we run multiple experiments and we'll change the concentration. So this is my only reactant, so this is a nice, easy one to study. I can go ahead and double the concentration of that reactant, and I'll measure the rate in the first time, I'll measure the rate in the second time, and from this data I can see as I double the concentration, I'm quadrupling the rate. And that tells me that actually this guy is involved twice in the mechanism. From seeing that, we'll see how that works soon. So this is how do we actually express what we're going to learn when we investigate how concentration affects rate. And that expression is the rate equation, or the rate law. And so that's a generic expression that's going to relate rate and concentrations with a K constant. So you'll have rate is equal to this K constant times concentration of A raised to some power. Notice that power has nothing to do with the coefficient. For example, if I have 2 moles of hydrogen plus 1 mole of oxygen, this 2 has nothing to do with whatever number goes up here. Okay, so I've got that times concentration of B raised to some power. And I'm saying that my catalyst is involved too, so we'll say times concentration of my catalyst raised to some power. Okay, so these exponents, the N, M, and P, those are called reaction orders. They're telling us if A is going to be first order, second order, 0 order, or some fraction. So if in the end, when I solve for these, if I get rate is equal to K times the concentration of A to the first and B to the second, and let's say there was no catalyst involved. If I got that, then I would say this rate law is first order with respect to A, it's second order with respect to B, and it's third order. I just add those up overall. And then it would be 0 order with respect to a catalyst, or to that catalyst. So unlikely that a catalyst is going to affect the rate. Let's see. And the only way you can actually figure this out is you have to do an experiment. So you actually have to go to lab, double the concentration, keep everything else the same, and see how doubling that concentration affects the rate.